Hi there, I'm back with more equations of lines in two-space. Um, so we talked about the vector equation of a line, the parametric equations of a line, and our third form of the equation of a line in terms of vectors is called a scalar equation of a line. And this one we're already familiar with. It's basically exactly the same as the standard form equation of a line that we know from grade 10. But there's going to be some special connection here to the vector equation of a line, which I'll show you in a minute. So first I want to finish example 2, which I did A, B, and D parts in my previous video. I'm now going to do example 2 part C. And so it asks us to get the scalar equation of a line from the parametric equations for L1. So one way that we can do this is simply to isolate the parameter in both parametric equations, since the parameter is the same. So if we isolate t in the first equation, we get t equals x minus 3 over 2. And in the second equation, we'll get t equals y plus 5 over 4. So just do the algebra slowly if you need to check that I'm right there. And since the t's are the same, then we can now make those equal and say that x minus 3 over 2 must then be equal to y plus 5 over 4. So this would be our scalar equation of a line, but let's put it into a form that we're more familiar with, which is this form here. And so to do that, first of all, we need to get rid of the fractions. So let me just rewrite it at the top of this page here. X minus 3 over 2 equals y plus 5 over 4. To get rid of the fractions in one step, I'm going to multiply by the common denominator, which is 8, on both sides of the equation. And I will reduce the denominators to get rid of them. And then I'll distribute on both sides of the equation. So it's going to be 4x minus 12 equals 2y plus 10. And to get it in standard form, or what we now call scalar form, scalar equation, then I'll bring all of the terms onto the left side and keep it in order of the x term plus or minus the y term plus or minus the constant term. Oh, sorry, I made a little arithmetic error here, which, as you know, I'm famous for. My arithmetic is not very strong. Luckily, my math skills are. Okay, and then since there's a common factor of 2 here, I'm just going to divide through by it just to make the coefficients smaller, easier to work with if I needed to do anything with this equation. So my scalar equation of the line comes out to 2x minus y minus 11. Now I want to show you something interesting here. Let's just go back for a second and get our direction vector for the line from the parametric equations. So it's 2, 4. So m is 2, 4. And then I want to look at the coefficients of x and y in my scalar equation. Since there's nothing here, it must be a 1. So let's write that in vector form. Sorry, it's negative 1, 2, negative 1. And I want to show you what happens if we take the dot product of these two vectors. So let's have a look at that. Let's see what result we get there. So m dot n, you remember back to chapter 7, which was your test yesterday, or 2 days ago, so you should remember. To do the dot product, it would be 4 minus 4, which equals 0. And what does that mean? Well, that means that m is perpendicular. Vector m, which is the direction vector of the line, is perpendicular to vector n, which is the vector created from the coefficients of the scalar equation of the line. So that's the reason why I called the vector n, because you'll remember from calculus that normal means perpendicular. And so since that vector 2, -1 is actually perpendicular to the direction vector of the line, then we can call it a normal to that vector. Perpendicular. There we go. Okay, so why am I telling you this? Good question. Because now we're going to skip down to example 3 and we're going to use this information. So in example 3, part D, I'm actually skipping A, B, and C because we kind of already talked about it. We are now given a line in scalar equation form, 4x plus 5y plus 20 equals 0, and we're asked to write the vector equation of the line. Well, what we just found out is that the coefficients of x and y here, let's call them a and b from the scalar equation form, and in this case they're 4, 5, create a vector that is perpendicular to a direction vector for the line, for the vector equation of the line. So if we can find any vector that is perpendicular to this normal vector to the line, then we will have a direction vector for the line. So how do we do that? Well, probably the easiest and quickest way to do it is just by inspection. So I need a vector that I'm going to dot with vector n, and the result will be 0. If that's the case, then we'll know that I have a vector that's perpendicular to n, which would then be a direction vector for the line. So if I just do this, I don't know if you remember, back a while ago, I think it was in beginning of chapter 7, where I talked about a vector called, no, I can't even remember what it's called now. Anyway, it was a vector where you take the components and you switch them and make one of them negative. Okay, I'm blanking on what it's called. Ridiculous. But anyway, when you dot these two vectors together, a, b, and b, negative a, then you will in fact always get 0, because it's going to be ab minus ba, and ab is the same as ba, so therefore that's 0. So all we need to do to find a vector perpendicular to n, 4, 5 is simply swap the position of the components and make one of them negative. Doesn't matter which one, just don't make them both negative because that won't work. So therefore, a possible direction vector for our line is negative 5, 4. It could also be 5, negative 4. Or any scalar multiple of that would work as well. So let's go over here and we'll use that negative 5, 4 to write the vector equation of the line now. So we have a direction vector for the line. What else do we need? We need a position vector for the line. Let's call it R1, R2. Well, a position vector for the line starts at the origin and ends at any point on the line. So do we know any point on the line? All we know so far is that the scalar equation of the line is 4x plus 5y plus 20 equals 0. But we could easily use that equation to get any point on the line. Let's say, for example, the x-intercept. So we would let y equal 0. And then the x-intercept would be 4x equals negative 20. x equals negative 5. Therefore, negative 5, 0 is a point on the line. And so I can use that as a direction, as a, a position vector for the line, which would be negative 5, 0. And so therefore, the vector equation of this line can be written as negative 5, 0 plus t times direction vector negative 5, 4. That's one possibility, but remember there are always infinitely many possibilities for the vector equation of a line. And so we could have chosen to do the x-intercept instead to get a different point on the line. Or we could have chosen any value we like for x and then get the corresponding value for y. And so obviously there are infinitely many points on the line as well, therefore infinitely many position vectors for the line. And any vector that is a scalar multiple of the direction vector would also be a direction vector for the line. And so therefore infinitely many possibilities for the vector equation of the line.